My first project out of school was to look at the feasibility of generating autoclavable design that would withstand the rigors of typical autoclaves in the hospital environment. And since then, I've been involved in at least a half a dozen additional autoclavable camera head designs. The virtues of autoclaving are, number one, that it's the most ubiquitous sterilization means worldwide for medical devices. It's inexpensive and it's environmentally friendly. So it's significant for Arthrex to be able to, with the most common and inexpensive sterilizer in the world, to produce a product that's consistent and can survive the rigors of autoclaving. The reason that we've endeavored so significantly and overcome the technical challenges to make autoclavable cameras is because of its usefulness to our hospital customers. Well, there's two significant challenges with autoclaving. Number one is heat, and steam is a great heat delivery mechanism. It creates a lot of energy and delivers it quickly to the devices that are within the sterilization chamber. And second is the penetration capability of steam is excellent, which is why it's such an effective sterilizer. But as well, it produces challenges for medical devices to withstand that penetrating capability and the heat shock. So both of those things have to be in close consideration for Arthrex when developing the camera head to survive autoclaving. And the challenges are fundamental to camera head design. So in the camera head design, there's two things that we need to make work. First, we have to get light into the system. And as well, we need to get electronic signals into and out of the system while maintaining this hermeticity. Hermeticity is an airtight seal, something that can withstand the penetrating capability of autoclaving. And a third challenge is enabling user functions so that the camera head is held by the surgeon, of course, in the sterile field, and the surgeon has to enable the proper optical image on the surgical monitor, and as well interact with the device, in particular the camera head buttons that enable the surgeon to take pictures or record video or other things that we enable through the camera system. Well, with a 4K system, the challenges for making an autoclavable system become even more significant. So to overcome those challenges, number one, we had to reconsider all of the optical design. And so the optical systems were completely reconsidered so as to optimize the image for 4K performance. Another significant challenge in making a 4K system autoclavable is that there's 4 times the number of pixels, and therefore the registration and precision of mounting these sensors relative to the optics is 4 times more critical. The processing challenge is now, again, 4 times as big. There's 4 times as much information. And lastly, not only does it have to function, it has to be ergonomically world-class. The testing that we've done to ensure that the system maintains its performance through its life after many autoclaves, the first step there is our design approach. We run autoclave cycles that are significantly longer than the expected life of the 4K camera heads to ensure the systems and the manufacturing techniques are robust to many autoclaves. In addition to extended autoclave testing, we do thermal shock testing, which is not necessarily consistent with typical hospital use, but it's a worst case test. We also test for even misuse of the device in the field. And last, we've done highly accelerated live testing. So that involves significant thermal challenges that are way in excess of the operating temperature, in combination with vibration testing and thermal excursions, both high and low. And while we continuously monitor the device to look for its performance, and our expectation and the result has been that the system maintains its performance and does not degrade even after all of those challenges.